this is a talk about scaling Django, but more in general about scaling any kind of web-based system. But first of all, who am I? I'm Andrew Godwin. I am a Django core developer. I have been for too long now, one might say. I also work at Eventbrite, doing sort of ticketing and back-end work there. And I'm perhaps most well known for Django's migration systems and now channels. But what I'm here to talk about is distributed systems. And firstly, I want to cover why they even exist. Why do we have systems that are distributed? Why not have synchronous systems that work purely in lockstep? We have none of these problems. Well, it starts with the speed of light, of course. This, for those who aren't aware, is how fast light travels. And it is against the laws of physics for any data to travel faster than this. Now, in reality, electronic signals in your computer travel about 2/3 this speed, so around 200 million meters per second. Now, this is related because the way computers work is in clock cycles. What happens inside your computer is that every clock cycle, the logic propagates one step. And so if you're cycling at 5 megahertz, that's 5 million times a second, that means that in that time, a signal can make it approximately 60 meters, which is quite far. You know, it's about as long as this hall here is. But modern CPUs are at 3 gigahertz. And so you have this problem where you only have about 10 centimeters, and that's the literal limit of the universe to send data between these clock ticks. And so in reality, this combined with our engineering means that we just can't write systems that run quickly that are synchronous. We have to have distributed stuff. Even inside your computer, you have distributed components. Multi-core processors are literally this. They are processors that are 2 or 4 or 8 cores on the same die, and they run often independently with different clock speeds. And so they already have a mini distributed system there passing messages to each other. And the key thing is that these systems are made of independent components. What that means is you can reason about each part of that system independently and treat it as its own thing and test it and try it out as its own thing. Now, you might ask, well, why isn't everything distributed? And the answer is they're not faster. They're slower and more difficult to write. If any of you have tried to write threaded code or networking code or similar, you will understand that it is very difficult to write that kind of code because the complexities involved. It'd be much easier for us as programmers if we just wrote simple, synchronous code everywhere. So then why do we write them at all? Well, the answer is they can be scaled up much further because we can take distributed systems and take them beyond that 10 centimeter limit. We can take them to a whole data center or a whole country or a whole globe. And that's kind of what I want to cover here in a small way. But first of all, we have to talk about trade-offs. So one of the things you get with distributed systems is that there is never a perfect solution. There is no possible way you can have all the things you want and no downsides. If any software claims to give you a perfect solution, don't trust them. They are lying to you. My favorite example of this is the product triangle. Fast, cheap, and good. You can have any two. If you have all three, it's impossible. And this is from project management. Often, if you're trying to write software, like, well, you can have it fast and cheap, but it won't be very good. Or you can have it good, and it's very cheap, but somehow very slowly. And this sort of common concept is there in a lot of trade-offs in programming. It's not always 3 items like this, but it's often that same kind of, well, we love all of the things, but you can't have one of them, so you need to choose to drop them. And so often in a startup, you will drop the good, because you don't have any money, you don't have any time, so you end up writing very fast software that's quite cheap and often not great. And then you spend the rest of your life paying for the not great part. And then companies often, well, they want it quite cheaply, they want it well, so it happens very slowly. So how does this all relate into Django? Well, Django is a pretty standard, is the wrong word, because it is kind of almost the example of Python web frameworks in a way. And a lot of people know how to basically scale Django. And if you don't, here's a quick idea of how to sort of scale Django. So Django starts off with WSGI workers. They are Python processes, they run on a machine, They use uWSGI or gUnicorn or ModWSGI or anything you like. And the first step is you have one box, and you go, oh, we have too much traffic. We will have multiple boxes, and we will put a load balancer in front of them. For this, please use HAProxy. It is highly recommended. And this is simple enough. And the reason we can do this is that HTTP, in its design, is shared nothing. Every request you get over HTTP contains all the information you need to serve it. Cookies are there. The host header is there. All the request body is there. And so you don't need to share anything between these servers. So what happens when you do? Let's take, for example, having a cache. So in this situation, we have a shared cache. Say there's a really expensive result we want to compute. Well, how do we take that cache and scale it? Like, it's fine for 3, but what if we have 300 workers? Because we can add hundreds of workers and not have a problem. HAProxy will happily deal with that kind of thing. But the cache just won't scale. And the key thing is a cache is actually also shared nothing. You can take the cache and you can split it to be 1 per machine or 1 per group of machines, and it will still work pretty much the same. As long as your requests are distributed evenly, you'll end up with about as good caching performance as you'd want, because if a really slow request keeps coming in, it will hit every server and it will fill the cache in that server. It's not quite as good. This is already a trade-off, but in practice, it's a pretty good start. But then let's think about databases. Now, you can't do the same with this as what I did here, because if you had a database per worker, when somebody saved a page and then loaded it again, it would maybe just have vanished because it's on a different database. So we need to take our database and we need to scale it. And this is kind of the essence of what's difficult about scaling Django and web applications. And the problem with scaling databases is something called the CAP theorem. I will point out this theorem is not scientific, and it's more sort of a guideline, but it's a good way of reasoning about it. So let's bring back the triangle. So the CAP theorem says that you can have any 2 of these 3. You can be partition tolerant. That means you can deal with a network that's latent or down. You can be available, which means that you will always answer a request, and that means answering without an error, crucially as well. And you can be consistent, which means that you read the same thing from everywhere in the graph. Databases can be at most 2 of these. That's what the theorem says. If a database claims all 3 of them, again, they're lying to you. Don't trust them. I will not mention certain databases that claim this. But let's think about each of them. So partition tolerance basically means, can you work over a network? Most modern databases are partition tolerant because otherwise they just wouldn't work. If you can't deal with latency, you're going to quickly decay into a load of unusable data. And so the real choice for us is between availability and consistency. Availability very much means that you can always answer requests, but at the expense of them being correct. So what that looks like, for example, is if a database is available but not consistent, I can always write to it, but then when I read it back, it might be an old value. So if you're writing a shopping cart, for example, this means that you might add something to the cart and then check out, but it's vanished from the cart, and then finish checking out, but it's reappeared in the cart, and you don't charge them any money for it, which is not great, obviously. But then again, what you can do is you can drop availability for consistency. And so you can say, well, the database won't always be there, but when it is there, I will have perfect consistency in my transactions. And so this is what Postgres is. Postgres and MySQL and most relational databases are roughly a CP. They are consistent and they are partition tolerant. This means that if you can write to them, if they're available, they will always give you an answer that is consistent across the entire set, and you can trust that what's in there is good. Now, this obviously has extra extensions into transactions and ACID and similar, but that's the basic summary. And as a contrast, we have Cassandra. Cassandra is AP. It is always available. You can write to any node in a Cassandra cluster, and they will always take your write. But it won't necessarily give you back the same answer. Like, if you write to node 1, and then you read from node 5, if it hasn't been enough time to propagate round, you will get the old answer that used to be in the value you wrote to. And really, the choice of which one of these you use is down to what you're designing. It can be very hard to design a product around inconsistency. And for this reason, most small companies opt for a consistent database like Postgres or MySQL, because you can reason about it very easily, you understand what's happening, and you don't need to design pages for, well, the user might see a thing, and then the next reload, the thing may have vanished, and then the next reload, it may have reappeared again, which is what happens on a consistent database. So for this reason, most people don't choose something like Cassandra or React, another example of this. But if you want to, those databases make it very easy to scale. Because of that trade-off of consistency, you can just add in a few thousand nodes into that cluster, and it will pretty much take the weight for you. But of course, if you're running a shopping cart or a ticketing system like I do at work, you really want consistency. You don't want to sell people tickets and have them vanish afterwards. So how do we take a relational database and find other solutions? Well, the most obvious first one, and the one that sort of I would recommend to all of you if you go this route, is read replicas. This is often called master-slave as well. And the idea here is that you start off with having a main database, which is, again, just Postgres or MySQL, and then replicas of it, like often called slaves. And what these do, these stream data from the main database into their own copy, and you can query them. And you can only query data from them. You can't write data to them. They are read-only. And so this is really good for scaling reads. If you're, say, Wikipedia, and you've got a very high read load compared to your write load, then this is perfect for scaling that kind of thing, because if pretty much everything is reads, and you can add these replicas pretty much forever. We have tens of them at work serving our sites. It works pretty well. But if your write load is heavy, this doesn't work. You can still only write to that middle server. You can't write anywhere else. And so as soon as you get over a critical number of writes, and in particular, as soon as you run out of Amazon boxes that are big enough to handle your service, because the cheap way is just increase the size of the database server until it stops working, you need to fix this. And there's also a second caveat to this. If you do this example, then you have a problem. And it's a consistency problem, because by making this system, you've made it very slightly inconsistent. So if you write to the main database, there is a small lag of a few seconds at most between it going into the main one and appearing in the replica. And if in that time, say you're, again, in a shopping cart, you save to your cart, which writes to the main, and then you want to just display the cart, which reads from a replica, you can actually show an old version of the data. And so for this reason, when somebody makes a request that writes to a table, you have to what's called pin all reads for that table to the master database for as long as that request is available, so that it looks like they have concurrent, consistent data. And this also is a load problem, because what you have is you have the problem of, well, now not only the writes, but any reads that are close to writes hit this main database, and you're quickly going to start running out of not only space, but things like your number of TCP connections can even be limited in these cases. And so when you get to this point, you end up having to really start thinking about sharding. Now, sharding is a term that is very generic. It can mean a lot of different things. What I'm going to cover here is a couple of different ways. So first of all, the easiest thing is sort of called vertical sharding. What this really means is just taking your different tables and putting them in different databases. This works very well if you have a couple of very big tables that are sort of equally sharing the main database. You can take all of your big ones, put them on their own server, and you're fine. The problem with this is they're on different servers, which means you can't join between them. And so if your site relies heavily on joins, you'll quickly find that, well, now I can't join the users table against the events table because they're on different ends of my data center. That's not possible. And so already you've lost some of the attraction of SQL. If you can't join, you have to sort of do one query to get all the users, bring it into Python, do another query to get all the events, bring it into Python, do a dictionary comprehension, join them together, and you might get there in the end. So that doesn't seem great. What's the other option? Well, the other option is horizontal sharding. And in particular, I'm talking about something called consistent hash sharding. So what you do is you have lots of databases that all have all of the tables, but what they have is a subset of the data. And the first thing to do with sharding like this is to pick how you divide the data. And this is often the thing people get wrong. So The best way of doing this is often by the user or by some sort of top-level object. So let's say we're going to divide it by user in this case. So we're going to take our user ID, we're going to apply a hash to it so that we get equal entropy, and we're going to take the first character of that hash and look it up. So what this means is, hopefully, if we chose our hash function correctly, we have all of our IDs, because of course numbers are all towards the beginning, they're like 1, 2, 3, 4, 5, go into an even distribution of hashes, which then evenly go into these shards. Now this ends up with roughly balanced databases with the right data in each of them, but you still have a problem with joins. So in this scenario, we do have all of the tables in each database, but we can't necessarily join between databases. And so as long as we're just querying only for things owned by one user, we know that, say, all of the user's tickets, all of that user's events are in the same shard, we can do joins as normal. But if we're trying to query across users, say we're trying to get a summary of 10 users' tickets, we then have to issue queries on all of the shards, take the results, and manually combine them again in Python to get a single valid list. Now this often ends up being better because usually you can split your product by something like users or companies or similar. But there are problems. In particular, you can have unbalanced shards. So imagine you have something like Instagram, and you have lots of users with like a few hundred followers. It's pretty normal. And then you have, say, Justin Timberlake joins. He has 10 million followers. And so now you have a small shard, a small shard, a small shard, and then a giant shard where that person happens to have landed on. And so you have these problems. And this happens too in other areas. Like, say you're doing ticketing and you have one company who's selling 1 million tickets. Then you have a problem with where to put them. And so one of the problems with this kind of sharding is trying to balance them out. And in particular, with consistent hash sharding, you have the problem that you don't get to choose which server these go onto. And so the trick here is often, rather than hash into, as I've shown here, like sort of 16, you take the ID or whatever you want, hash it down into around 4,096 buckets is a good number, and then you have these 4,000 logical shards, and you map them down into physical shards. Say, well, shards 1 through 1,000 are on this server. And then if one of them gets really big, you can manually say, oh, but shard 300 is actually over on this server. That's a good way of being flexible. But of course, this also only gets you so far. And so then you need both of them. You need to have vertical shards of each of your tables, which themselves have horizontal shards of each of their things. And you quickly descend into a nightmare of which of my 100 databases do I contact? How do I understand all of this? And of course, to be more efficient, you want a cache. Well, let's add a cache onto the end of this. And so you start seeing the problem that you have at scale. And this is not just a problem of programming complexity, it's a problem of understanding. You've got to remember that when you have a small project, a small piece of code, you can understand all of the code. Like as a programmer, as an engineer, you can understand the entire world of that code. When it gets bigger and bigger, you have no chance. Like at work, we have a code base that is so big that no one person can understand any of it. And it's even more true of, say, Google or Facebook or similar. And so you have a problem not only of scaling the database, but of scaling your logic of your teams. Like no one in a big company or in a big product should have to understand everything. There should be somebody who understands the general layout. You have what's called a software architect. They know only a high level, but they don't know any details. They all know how things talk to each other. And so what do you do now? Like, how do you solve this problem of having 20, 100, 1,000 databases? Well, this is where you bring in often a concept called services, or microservices, you may have heard them called. The micro is a prefix I'm not particularly a fan of. It sort of just means, oh, they're smaller, but smaller than what? They're smaller than code, sure. And what services are is a way of taking both your data and your business logic, your Python code, and splitting them out into separate sort of silos. And so in that example we had there, we could take our databases as well as the code that talks to them, that understands the sharding, that does things like, oh, when I change a password, I set the hash, and wrap it all in what's called a service. And this lets us then take those things and reason about them as black boxes, as opaque boxes. And so we can say, well, this team understands the user service. They understand how to talk to it, they understand how it works, and the rest of us can ignore it. All we need to know is that we can say, hey, make a user, hey, delete a user, hey, change a password. That's all we know. And then as somebody outside that system, we can then reason much more easily about this system. Like how it implements that stuff, we don't care about. All we care about is that it fulfills a contract. And as long as that's good, we can write against it. And so you end up with each of these services being its own smaller project. And in fact, what you've kind of done is you've made your own specialized data store. You've taken databases or Redis or similar, you've encapsulated it with extra code, and you've made a new kind of data store just for the thing you're storing, like tailored to your business logic. This can be not only databases, it can be queuing, it can be things like a fire hose of all the events, it can be things like locking and unlocking of inventory. And so you get a lot of flexibility in how you do this stuff. But of course, you have a problem. You have services. They probably run on different clusters. How do you talk between them? How do you say, when I make a user, make them a password if it's separate? If I make an event, how do I make tickets for that event? These are on separate stores now. It's like the join problem earlier, but even larger. Not only can we not join, we can't even talk between databases. We have to sort of stand back and go, oh, we need to talk at the high level of services. So the obvious option here is just talking directly between them. Each service knows where the other services are, just sends a request, probably over HTTP, to that service. Seems great, you know, simple enough, 3 lines, what could go wrong? Well, let's have 5. Oh dear, there's now 10 lines there. Well, let's go up to, it can't get worse, let's go to 8, oh dear. And so this is, you know, this is a quadratically increasing number of connections. If you have 20 services, you have 190 connections. If you have 100 services, I haven't even calculated that out if you want to. In Python, you can do sum of range of a number, and it tells you this number. I have heard some companies have over 1,000 services. You can imagine it's impossible to do this with 1,000 services. So how do you solve this problem? How do you take all these services and try and route them to each other? Well, the first obvious thing you can try and do is have a central place they all talk to, a router. You say, hey, I have this message for this service, and it sort of opens a TCP connection and just like, a bit like HA proxy, routes it through to the right place. That works pretty well. You still have the problems of having connections, though. In particular, if you try and connect and the service isn't there, or it's being restarted, you're going to lose your message. And so the slightly better version of this is the message bus. And the message bus is the same idea. It's still a central point that you talk to, but that point also gains things like queuing and routing and a bit more logic to itself. And the idea here is that a service can just write to the bus, say, hello, I have a message request for service 2. The request is to make a user, and when you finish, can you send it back to service 1 with this endpoint? And this, of course, makes something that every programmer fears a single point of failure. And if you are like me, you have it drilled into you that single points of failure are the work of the devil. They are terrible. They should never happen. This is not true. A single point of failure is sometimes bad. It's not all bad. And you have to consider. So let's think about this again. We have a mesh network, and mesh networks seem good. But what you have, as we learned yesterday, is you actually have 20 or 30 different points of failure. And I can guarantee you that you will, if you have one of them, monitor that incessantly. You will understand it, you will know how it works, you know its limitations. You have a team of 5 people just watching it all day and all night. If you have 20 of them, you don't have 20 people watching each of them independently. You're not going to notice as much. And so often having a single point of failure that's really well understood, that's really well monitored and known, is better. Like, you can have one of these, and like we have one and a hot standby. So if it fails, we can switch it over within a few seconds. But having that single point of failure is good because it's not only a place to route things through, but understand. As a developer of a service, all you know is, well, hello, I'm developing this service. All I need is one thing, the IP address of the message bus. I don't need to know what services are there. I don't need discovery. All I need to know is, hey, I send things over here. I receive things from here. That's it. And if you're scaling things out as well in terms of connections, this is great. You can just have an image that says, oh, boot up this image of this service, connect to this bus, and off you go. No need to update a router or a proxy or anything like that. And so, obviously, I'm a fan of this. That's why I'm talking about it. And this is kind of what Django Channels is based on. So a lot of people think that Django Channels is about WebSockets only. And that, indeed, was where it started. But what Django Channels is actually a set of things. It is both WebSocket handling, but underneath it has a message bus. And the way it makes Django work, the way that everything is asynchronous, is because it rewrites Django to run like this on a message bus. In particular, what happens is we have our HTTP server as one thing on the bus, and Django workers on the other parts of the bus. So this means that this part, the server that terminates HTTP and WebSockets, is written in Twisted. It's fully asynchronous. It can handle thousands of connections by itself without any threading. And the Django workers are synchronous. They are old Django. They do one request at a time. But because all the asynchrony is handled on the bus, we can have what looks like WebSockets, but handle it synchronously in Django without rewriting all of Django, which, in case you're not aware, is probably a 4 or 5 year long project. So we don't want to do that. And in particular, it has those trade-offs. So when you pick a message bus, like with any solution that's distributed systems, you must pick some trade-offs. And what I've tried to do here is make a message bus and a Python interface that captures what I think and what I believe is the best set of those trade-offs that you can pick. You may disagree. No one is the same. But my goal here is to have a solution that, like Django, is good for about 80% of people. Not 100%, about 80%. So this is how people think of channels. We have Django up here. We have a channels library. And then what you don't know about is this thing here. So channels is a library that sort of just links to Django, understands how to decode things into Django requests and Django responses. Underneath it is a separate abstraction called ASGI, which is definitely not based on WSGI, for reference. And what that is it's a sort of abstraction of message buses. It has send, it has receive, it has a few other things, that's about it. And then what this does, it backs onto something behind it. So the most common one we see here is one that backs onto Redis, but there's also one for RabbitMQ and a few other ones for testing. And so what you can do is you can take this and you can actually take away Django. You can just run pure Python on top of this and have pure Python message buses. And this is what we're doing at work. Our services are just pure Python, occasionally using the Django ORM, because we like Django's ORM, but directly on top of the channel layer. And so what we can do is we can say, well, actually, we just have these Python processes that run and talk to each other over this thing, and it's maintained by Django, right? Like this is part of the Django Channels project. It's maintained, it's tested, the security releases. Sure, I do most of that stuff, but there's a guarantee there. So it's a really good way of writing it. But let's talk about those trade-offs. So first of all, the most important thing is how you fail. Again, if someone claims to deliver messages exactly once on a queue, they're lying to you. It's good fun, this, isn't it? So your choice is, when you have a queue and it fails to deliver, how does it fail? Well, the obvious one that you think of first is that it delivers at most once. That is, if it fails to deliver, the message vanishes, never to be seen again. This is how your sort of simple queue would work, say, like if you use a database. You would sort of write a row in the database, and then your worker would just read a row and delete it when it reads it. And if you read a row and delete it, and then the process crashes, you've lost the message. So that's at most once. The other option is something called at least once, which means when you fail, you redeliver, you try again. And what this means is you can get duplication. So for example, Kafka does this. Celery in some modes does this too. So this means that what you do is you read a row, and then you process it, and then you delete it once it's finished processing. And so what this means is if you read a row and process it and then die just before you delete it,
Another thing comes along and goes, well, it hasn't been done yet, and also runs it and then tries to delete it. And you've run things twice. I believe in software that's designed to deal with loss and crashes, and so given that, I personally believe that at most once is easier to write for. You should already be able to deal with things disappearing, so why not have that just be the same as your message queue? If you do at least once, you have to write code that deals with deduplication. Say you're sort of charging credit cards or taking payment. If you have this, you might charge somebody twice. And I would rather not charge somebody than charge them twice. The next thing is guarantees. The way channels is designed, it is a very, very low latency queue. The end-to-end response time is around 1 or 2 milliseconds, which is very reasonable for a network. The trade-off here is that because it's so low latency, we sacrifice some reliability, some persistence. And so, yes, it's very quick, but there's a slightly higher percentage of them that go missing. So it's like 99.99% delivered than there was something like Celery, for example. Celery has a very low loss rate. It has a lot more sort of negotiation and understanding, but the latency is higher because of that. Like you're looking at probably a tenth to half, maybe even a full second or two. And because channels is a message bus that powers sockets and WebSockets, we need that low latency. And so for that reason, it's designed specifically to be something to communicate fast rather than sort of a slow task kind of queue. The other thing is queuing type. So the obvious thing for a queue, and what a queue is the first thing in, the first thing out. The head of the queue has been there the longest, and then when you go and fetch it, you get the oldest thing in the queue. This is good for consistency. It means that everyone in the queue gets the same experience. Everyone is equal, basically. But it can have problems during big backlogs, because if you get a queue that's 100 or 200 items long, and it takes a couple of seconds to get through that queue, everyone on your site will have a couple of seconds of latency. Like, it'd be bad for everyone. The opposite is first in, last out. It's a stack, right? The first thing in, the oldest thing, is the very last thing that's pulled out. And what this ends up being is, it may seem bad at first, but it ends up having good responsiveness for everyone that's coming new to the site. If you backlog, the stack grows in a huge amount downwards, but everyone who turns up after that still gets served pretty quickly. And then you just time out the people who are slow, and then drop them. So what happens is you make a totally terrible experience for a small number of users, but keep a great experience for everybody else. Personally, I prefer the easiness and simplicity of first in, first out, especially as long as you have a queue that is rapid and going through quickly. First in, first out is much better at just giving you predictable understanding information. It's quite possible that if you're just on the edge of how fast you can process, this can make like 1 in 10 pages just not render, which is not good. The last thing here is queue sizing. As we heard yesterday, queues should definitely have a size. So for reference, if you don't have a size on your queues, they're infinite, well, that means that you don't have to deal with failure to send. You can always just shove things on the queue and go on and keep processing. What this means is, if you have a load of traffic or an error or something goes down, your queue gets longer and longer and longer. People who turn up get slower and slower and slower, and it ends up having a really bad time. What you can do, if you really want to, is combine infinite queues with first in, last out with a stack. That actually works quite well, as long as you time out things that are sort of a certain amount old. But given we're choosing the first one here, having finite queues is good. And what channels has is each channel that you send on has a capacity. It's about 100 by default. And if it doesn't fit on the channel, you get an error saying channel full. And your application deals with that. So say you're trying to open a HTTP connection to Django, which is going through channels. If the channel is full, it means that the workers are completely full. They have no room left to process. And so what we do is we say, oh, well, we return a 503, service unavailable. The same thing that HA proxy would return if it worked out it had 2 big queues as well. Whereas if we're trying to process a payment and we see the channel is full, we can go, well, we don't care about speed. We just want to have it happen. So we just sit there and wait and wait. When it opens up again, we can put the thing onto the channel, and we're good. And so the common theme here is you've got to understand what you're making. This is, as it says here, surprisingly uncommon. Most engineers don't know what they're making in its full extent. which is somewhat normal, especially for startups and new companies. You don't know entirely what you're making, but often you want to at least have an understanding. Try and sit down and sketch out the rough set of failure cases and how it should work. And once you understand that, you can go through and be informed about which trade-offs to pick. Now, I've shown you some here. There is a whole load of different ones in distributed systems. It's a huge field with many different problems. But the first thing to think about in those meetings about trade-offs is, what's your priority? Is your priority to have a perfect system that's really well built, but is slow? Remember the fast, good, cheap triangle? Huh? Or is your goal to get something that ships and works? And if you want the second thing, and you probably do, here are some tips. First of all, always try and design as much as possible around shared nothing. Try and make all the information you need to process a request or any kind of message in that message. Some good examples of this are Django signed cookies. What Django by default does is Django has a session ID and a cookie, and you do a request. Django goes, session ID, goes and queries a database, yanks out JSON, decodes the JSON, and that's your session. But what you can do is you can put all that session data in the cookie, as long as it's small enough. And then what happens is you have a request, and you have the data already. There's no database to hit. There's a security issue there, of course, which is, well, if the session is just in the cookie, the end user can just edit their session, which is why you sign it. So what you do is you have a cryptographic signature that says, well, we gave this cookie to you, we've signed it, you can't edit it, or the signature is invalid, so we trust it. And this is true of other things. So I showed you before the per-machine caches. This is a perfect way of having sort of shared nothing caches as well. Another top trick with caches is, say you have a site that gets really large load spikes on a couple of pages. A 1 second cache is incredibly effective at that kind of thing. If your job is to make it look always as new as possible, but stop huge spikes, just a couple of seconds of cache will give you from 100 requests a second down to 1 request a second on your backend, which can make the difference. And it will still look pretty live. It's updating all the time. Another thing, for example, is thumbnailing. So often when you upload a media file, people will, we'll take that media file and we'll go and thumbnail it now. We'll just sort of send it off to a Celery job or something and thumbnail it. If that fails, that's a big shared resource, what happens? Do you sort of show the user an empty page? The alternative is, there's a couple of Python services or commercial services that thumbnail on demand. When you request the image, you say, I want an image at this size with this cropping in the center. And it's all in the URL. It's all in one place. And then you can take that, make the thumbnail, often from a cache, obviously, and then bring it through in one go. And by doing this, you're taking all of this stuff and splitting it out. So if you see something that looks like it's shared, that like, all of my workers are talking to this, try and split it out. Try and take it and tease it apart into different pieces. If it still has to be shared, then you have to start sharding it, because you can't have a single shared resource in a big system. It's just not possible. And I spoke earlier about some sharding. Sharding itself is probably a few hours of talks as well. There's plenty of stuff online to go and read up about, but it's a good general idea. Like, one of these two things is usually what you want to try and go for. And among all of this, people think, well, I'm changing my site too much. I'm taking Django and ripping things out. Now, as a core developer, I want to reassure you, Django's job is to be deleted piece by piece. Nobody at scale runs Django exactly as we give it to you out of the box. That's not what happens. Like, Instagram does not run normal Django. What they do is they take Django and you replace each piece slowly to be something specialized to you. As I said before, Django is designed for the 80%, the general set of engineers. And as you specialize, our job is to sort of just fall away and let you do what you think is best in its place. And what you can end up with is something that has no Django code at all, but still looks like Django because, well, it started off being Django, and you've replaced every piece of it, but much like the broom where you replace the handle, then you replace the head, it's still a broom, it's still your broom. So don't be worried about taking Django like, we need a different caching layer, that's fine. We need a different session layer, that's okay. People replace the ORM, right? Like, if you go and listen to Carl's talk about Instagram from a previous DjangoCon, he will tell you about how they've entirely removed the Django ORM from Instagram. They all run against the custom Facebook store. But it's still Django. There's still like URL routing in there. So this is fine. And it applies to other frameworks too. But the key thing is, when you do this, make sure you understand what you're replacing. I've seen many people take Django and go, oh, we're just going to replace this with something else. And they got it mostly right, but not 100% right. And we have good documentation about what this is meant to be. So if you do replace pieces, please try and understand like what the caching layer looks like. I've seen examples like, oh, we just used this thing wrongly, and now when I write to the cache, everything else in the same thread gets the same response back. And like, I start getting like pictures in my header and stuff. And then my final piece of advice to you is something very important. Don't try this too early. This talk is from a place of, Eventbrite is a reasonably large company now. We have hundreds of engineers. You can't do this when you're small. You will not only struggle to do it with the number of people you have, but you'll probably pick the wrong trade-offs. You don't know what your problems are until you see them. What you should do is see them coming and go, our database is getting very busy, and then handle them in advance, rather than going, oh no, it crashed, how do we fix it? But you won't know until you get at least near there. What you can do, however, is take these ideas of having things separable and separate and building them sort of as service-like things and apply them to a new project. For example, if you're writing a new Django project and you have a couple of apps, like a user app and events app, try and keep them self-contained. Try and not have them import each other. Because if you keep them like that, when it comes time to make them separate, you can go, oh, well, it just imports itself. We can just lift out this module and put it down separately and hook it in and we're done. Otherwise, you spend weeks or even months of like going through the thing, removing imports, adding different connections in, trying to fix it up, and trust me, it's painful doing all that stuff. So just consider it, try and think of it, but don't go down the road too far. Don't shard from day one. You won't need it. The best advice for a small company to scale the database is to buy a bigger server. It's very cost effective, trust me. And thank you.
Hello.
Hello.
Thank you for the talk. And my question is, how can you say something about how big Eventbrite is in terms of, I don't know, users requests per second, something like that? When do you need to, like, how much load do you have that you need to scale in this way?
So I can't give specific numbers, unfortunately. One of the things we're not allowed to tell you. But my general advice to you is probably around 10 servers. Or like, say in particular, I used to run a site, Minecraft forums, in fact, that was a huge amount of load, but very heavy read. That was just 3 or 4 servers. It was 3 PHP servers and 1 database. We just kept increasing the size. Like, we went to software and went, oh, can we have a really, really big machine with like 4 processors and loads of RAM? Like, sure, if you pay us the money. And that worked fine. So I'd say like 4 to 10 servers is sort of the point where you start thinking about it, like sort of a few tens to hundreds of requests a second. But it really depends on what you're making. If you're making like shopping, it comes much earlier. If you're making like a wiki, it comes much later. So it really is, unfortunately, I can't give super amazing advice on that. Anybody else?
Hey, thanks for an amazing talk. What I wanted to ask is about the bus, and especially about the channels, and Django channels. Yeah. So the question is, how do you? Is there a way to have something like sticky session or routing in the channels, and how does that affect the complexity of the bus itself? How do you think about it?
That's a very good question. And this is about what I said about shared nothing. So your first thing would be, oh, well, what if we have all the things from one socket of stickiness go to the same server? We can store things in the server memory. But I'm like, well, that thing could crash. We shouldn't store them there. What Channels does is it uses the Django sessions framework. So it takes each WebSocket, or each sort of incoming socket, and gives it a unique identifier, which works like a session ID. And then in Django, you have a decorator, which just takes that reply channel, as it's called, and just looks up in the sessions table and gives you a session. And so what you can do is you just say, oh, you do @channel session, you write some code as normal, you store things in a session, and then the next thing on the next server, which could be the other end of the rack, can just read it from sessions and handle it. So that's kind of how we solve that, trying to reuse as much Django as we can. But again, it may not work for you, but you can just replace it. It's an optional part. Any more?
Thank you.
Oh, thank you very much.